Do you ever stop to think that there's this invisible force all around us that's trillions of times stronger than gravity? I mean, a force that literally builds the world, holds atoms and molecules together, the whole shebang. Well, today we're pulling back the curtain on that force. We're going to dive into the one rule that governs it all, Coulomb's law. Okay, so we all get gravity, right? It just pulls. That's its one move. But the electric force? Oh, it's way more interesting. It's a two-way street. It can pull things together, sure, but it can also push them apart. And that little difference, that push and pull, is what makes our world so incredibly dynamic. Now, if this whole idea of a fundamental force sounds kind of familiar, it definitely should. You know how Isaac Newton gave us the universal law for gravity? Well, a French physicist named Charles-Augustin de Coulomb did the exact same thing for electricity. And honestly, when you see his law, it's almost like he was peeking at Newton's homework.
I mean, just look at that. Side by side, they are practically twins. Newton's law on the left is all about the mass of two objects. Coulomb's law on the right, it's all about the charge of two objects. But the structure, especially how they both depend on the distance squared, it's the same blueprint. And that makes this whole thing way less intimidating to figure out.
So, let's pop the hood on this new formula. We're going to take it apart, piece by piece, and really understand what each little symbol is telling us about how this incredible force actually works in the real world. And here it is, Fe equals K times Q times Q, all of that divided by d squared. It looks simple, and it kind of is. This one little equation is our key to calculating the electrostatic force, you know, that push or that pull, between any two charged things anywhere in the universe. First up, we've got Q and Q. These are just the amount of electric charge on our two objects. And the rule here is super straightforward. The more charge you've got, the more force you get. You double the charge on one of them, you double the force. Easy enough. Next up is D, the distance between the charges. And this, my friends, is where things get really, really interesting. Unlike charge, where it's a simple one-to-one relationship, distance has a much, much more dramatic effect on the force. It's something called an inverse square relationship. Let's see what that actually means.
And finally, there's K, Coulomb's constant.
Think of it as just a conversion factor that makes the units work out. But look at the size of it. It's almost 9 times billion. That massive number should be a huge clue, a little alarm bell, telling you just how ridiculously strong this electric force is compared to anything else. Okay, so we've got the recipe, we know the ingredients, now let's see what happens when we actually start cooking with it. What happens when we play around with these variables? It all boils down to a few very simple rules. And here is the single biggest difference between this and gravity. The direction of the force totally depends on the type of charge. If the charges are the same, say 2 positives or 2 negatives, they push each other away. They repel. But if they're opposites, 1 positive and 1 negative, they pull toward each other. They attract. It's really that simple. Opposites attract, likes repel. This table lays it all out perfectly. Double one charge, you get twice the force. Double both charges, you get 4 times the force. But now, look at the distance. Whoa! You double the distance and the force gets 4 times weaker. You triple it and it's 9 times weaker. That d squared in the denominator is a total game changer. All right, let's do a quick gut check. Based on what we just saw, what do you think happens to the force if we take 2 little charges and move them from 10 centimeters apart all the way out to 30 centimeters apart? Yup, you got it. The force becomes 9 times weaker. Because we made the distance 3 times bigger, we have to square that 3, which is 9, and because distance is on the bottom of the equation, the force drops by a factor of 9. And that right there is the famous inverse square law. Pretty cool, right? So we've talked about the rules, but you know, talk is cheap. Let's see just how insanely powerful this force really is. Let's pit it head-to-head against gravity in a little cosmic showdown. Let's zoom way, way in to a single hydrogen atom. You've got 1 proton in the middle and 1 electron zipping around it. Now, both of these particles have mass, so gravity is pulling them together. But they also both have charge, so the electric force is pulling them together too. So the question is, who's winning this tug-of-war? The electric force is stronger. How much stronger, you ask? Well, this much stronger. That number on your screen is 2.3 times 10 to the 39th power. That's a 2 with 39 zeros after it. It's a number so big we don't even have a good name for it. It's not a competition, it's a complete and total knockout.
To try and put that in perspective, if we made a bar chart where the force of gravity was like 1 inch tall, the bar for the electric force would stretch for billions and billions of light years. We can't even draw it to scale. In the world of the atom, gravity is so weak it's basically a rounding error. It doesn't even matter.
And this brings up a huge, fascinating question. If the electric force is so mind-bogglingly, absurdly powerful, then why isn't it the boss of the universe? Why do we notice gravity every single day, but not this?
Let's ask it directly. We all feel the Earth's gravity pulling on us. But if the electric force is so much stronger, why don't we feel a massive electric pull or push from the Earth? What's going on?
And the answer is one beautiful, simple word: balance. Most things in the universe, including you, me, and the entire Earth, are electrically neutral. They have an almost perfect balance of positive and negative charges. So all those immense, incredible forces are still there. They're just locked in a cosmic stalemate, canceling each other out. And that lets the weakest force, gravity, take over the large-scale show.
So let's do a super quick recap. Coulomb's law gives us the rules for the force between charges. That force is special because it can both attract and repel. It follows that powerful inverse square law, meaning it gets weak really fast with distance. It is profoundly, unbelievably stronger than gravity, and its incredible power is hidden in plain sight, all thanks to neutrality.
When you get right down to it, this isn't just some dusty old equation. This force is the silent architect of our reality. It's in every chemical bond, every molecule of water, and it's literally what's making the neurons fire in your brain right now. It's the balanced, invisible power that makes everything possible.
And that leaves us with one last really fun question to think about. If our whole world is built on this force being kept in perfect balance, what happens on those rare, dramatic occasions when that balance is broken, even for just a split second? Something to think about.